Okay, this is your first lesson in Chapter 8, Sequences. You will use sequence notation to write the terms of sequences. Use factorial notation. Okay, first we're going to look at some sequences. These sequences, try your best to get the next two terms. Don't just watch these. See if you can actually figure it out, because this is going to be very important for this lesson. And we're not going to get a whole lot of chance for you to practice. So this is one of the few times. So to figure out what 1, 4, 7, 10, what would be the next one here? All right, 13. What do you think comes after 13? 16. Okay, so what I would do is I would pause this, see if you can figure all these out. If not, then watch one of them pop up at a time, and once you see something, trying to guess the rest. Okay. And number 1, you're just going up by 3 each time, right? What about this one? What about this one? You have 1, 4, 9, and 16. Okay, the next one's 25. Next one after that is 36. We added 3, added 5, add 7, add 11, add 9, add 11. So we're adding basically the odd numbers. But there's another way to think about this sequence, is that this is 1 times 1, this is 2 times 2, 3 times 3, 4 times 4, 5 times 5, and 6 times 6, or 6 squared, 5 squared, 4 squared, 3 squared. Different ways to see this, and if you can see through these patterns, then you'll be able to write them algebraically. Okay, 1, 5, 11, and 19. What comes after 19? 29, 41. So we added 4, we added 6, we add 8, we add 10, we add 12. About this. Okay, we went down by it looks like 32. Then went down by 16. Then we went down by 8. Then we went down by 4, right? Or we can say we added a negative 32, added a negative 16, added a negative 8, added a negative 4, so we should add a negative 2. All right, what about 10, 7, 4, 1? Okay, so this will be 10 to 7 is minus 3, minus 3, minus 3, or add a negative 3, and if you add another negative 3, you should get negative 5. All right, sequences versus series. What is a sequence and what is a series? What's the difference between a sequence and a series? A sequence is a bunch of individual numbers in a particular order. A series is a bunch of numbers added together, where the order doesn't really matter as much, although we get the numbers from a certain pattern up here. But the order of this would be very important. If I scramble like these two numbers or these two numbers and I ask you to find the next one, it would be very difficult to find the next one if these were not in order. So the order is very important. Since we're just adding these, the order of this is not important in a series. All right, an infinite series. Infinite series just means that there is no end. The first number, the next number, okay, the little number under here tells you which number you're talking about. This is the number 1, or the first number, and then the second number, the third number, and the number 4, the fourth number. Or in other words, like if you had a little tick number machine, a little ticket machine, this would be ticket number 1, 2, 3, 4, and so on. And because it's infinite, sequence, that means it just goes on dot 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 forever. There's no end. All right. So in this case, we have n. That's usually, we think of that as an x and y. So this is your domain and your range, or input and output. So this is the ticket number. This is ticket number 1, that's the number. Ticket number 2, that's the number. Ticket number 3, and that's the number. You can think of it as in a line, right? And if n is equal to 1, that's the guy with the first ticket number. And ticket number 2 would be n would be equal to 2, and so on. And this is the concept I need for you to get here. The nth ticket is the nth person. So if n is 5, then it would be 1, 2, 3, 4, 5 would be fifth person in line. Okay? So, or the fifth number in this sequence. All right, give the nth term, or given the nth term. So this expression here is any term, and I want you to give me the first 4 terms. So to get the first term, you would give this one a ticket number 1, so 1 times 3 is 3 minus 2 is 1. Okay, this would be the first number. The second number would be putting a 2 in here. 2 times 3 is 6, 6 minus 2 is 4. The third number would be 3 times 3 is 9, minus 2 is 7. And the fourth number would be 3 times 4 minus 2 is 10. Okay, pause the video and give me the first four terms for both of these expressions. All right, so if n was 1, this was the first 4 terms. If n was 1, then there'll be 3 plus -1 to the 1 power, which is just 2. If n was 2, then it would be 3 plus 1 squared would be 4. If n was 3, then it will be -1 to the third power, which is -1. That will give you 2 again. And then the fourth one would be 4 again. So it's going to be 2, 4, 2, 4, 2, 4, 2, 4. And later on, when I give you a pattern like this, you'll know that the negative was to an exponent, which made it positive and negative, switching back and forth. And that's how you get numbers like that. Okay, it's important to see the patterns, because pretty soon I'm going to give you these numbers and you have to come up with the nth term. Okay, given this nth term, what are the first 4 terms? Well, the first one is going to be -1. Second one is 1/3. -1/5. +1/7. You notice that these alternate in sign. Okay. So that -1 to the nth power, that gives you the alternating sign. That's another way to get a positive and negative in your sequence. All right, here we go. Write an expression for the apparent nth term. The apparent, that means apparently what could it possibly be, because there could be more than one answer. But most of the ones I'm going to give you are going to be pretty specific, so there's one answer. But there might be another way to write that expression. So you have 1, 3, 5, and 7. Okay, how would you write the nth term? Well, let's see. Here's the thinking behind this. If you're going up each time by the same number, okay, n would be the ticket number would be, this is the guy with the first ticket, second ticket, third ticket, fourth ticket, right? So if you're going up by the same number, then we call this is a linear sequence, because there's a thing here that's a slope. And if you write that in slope-intercept form, you know that's going to be 2n, 2 times n, right? N's your input, your domain, or your x, plus something, your y-intercept. So all you have to do is go back and go, well, if n is 1 times 2, but I get a 1, and n is 2, 2 times 2, but I get a 3. If I go 2 times 3, and I get a 5, what would that be? Well, you can figure that out as a negative 1. Or you can use some algebra if you want. You can plug in the 7 for here, a to the nth, and then the 4 here, and then solve for that, right? It'll be 2 times 4 is 8. 8 plus what is 7, so it has to be a negative 1. What if you get one like this, where we don't have a common increment each time? Well, then you're going to have to think about it and go, well, this would be possibly exponential. Okay, it's not linear, but it's probably or usually exponential. See if you can go up another level. See if there's a common difference between these numbers. Okay, the differences of the differences is positive 2. So that tells me that this is going to be an exponential where the exponent is the 2 now. Okay, that's going to be your exponent. Once you go down one level, so now I know that it's 8n is equal to n squared plus something. Okay, and what is that something? Well, let's plug in a number. 2 squared is equal, 1 squared is equal to 2, and 2 squared plus something is equal to 5. 3 squared plus something is equal to 10, and 4 squared plus something is equal to 17. What would that be? I think that would be a 1, right? 4 squared is 16 plus 1 is 17. Okay, so you need to be able to come up with these things here. Okay, sometimes it might be tricky. You might get an exponent plus there's some kind of coefficient up here. It could be another number like 3 times n squared plus something. So you have to kind of be smart and clever and figure this out with a little creativity. All right, what if you are asked to find something like this? 2, 1.5, 1.3 repeating, 1.25 repeating. So we're going to find the nth term, okay? So first thing to try is look at this, and I don't know, it looks kind of screwy to me. It looks like they are getting smaller from 2 to 1 1/4, right? 2, 1 1/2, 1 1/3, 1 1/4, so they're getting smaller. But I'm going to write these all as fractions. So 2 over 1, this is 3 over 2, this is 4/3, this is 5/4, and then you can start saying, hey, if this is the nth term, all these are the nth term, and n is 1, so pretty much you can say that n is the denominator, and on top, it's always 1 more than that, so it'll be n, or 1, 1 plus 1, and then 2, 2 plus 1, 3, 3 plus 1. So it'll just be n plus 1 over n. All right, recursive sequences. Recursive sequences is that they give you a term for the next one. You notice that this is this one added by 1 more, so this gives you the next one, right? If this is the person with the 5th ticket, this would be the person with the 6th ticket. So if the first one is 24, the person with the 2nd ticket has to be 24 minus 3, which is 21. So let's fill this out. So the first one is this one, and this is the next one. So it'll be 24 is the first one, and then the second one will be 21, and the next one should be 18, because each one I'm subtracting by 3. Okay, and 15 and 12. Or if you look at this, you're going to say, how do I get the next one? Subtract 3. That's all this is. How do I get the next one? This tells you how to get the next one. Subtract by 3. Okay, let's try one more. Okay, if this is this one, the first one, this is how you can get the next one. And multiply by half. So the first one's 64. The next one has to be 32. The next one will be, half of that would be 16. Half of that is 8. Half of that is 4, and so on. Okay? So that's how you use the recursive. This just gives you the next one. What are you going to do to this one to get the next one? That's all. One sequence I want to talk about here, the Fibonacci sequence. If you, had math classes where the teachers talked about patterns, I'm sure they've talked about the Fibonacci sequence. It's you've seen it in the Da Vinci Code, the movie and the book. Played a major plot line, and also it's the sequence that happens in nature. Okay, this is how things grow. You take the 1 plus the 1, and you get the next one. You get 2. You always get the next one by adding the last 2. So 1 plus 1 is 2. Then 1 plus 2 is 3. 2 plus 3 is 5. Okay, and then 3 plus 5 is 8, and so on. So what will be the next one? 5 plus 8 is going to be 13. So 13 would be the next one in the Fibonacci sequence. Factorials. Factorial. A number with an exclamation point after it is called a factorial. And that means it's 1 times 2 times 3 times ... all the way up to that number. So 2 factorial is just 1 times 2 is equal to 2, up to that number, up to the 2. And note, this is pretty important here. There's no logical reason why 0 factorial is 1, but it's how it makes all of this work together. Okay, I've been asked a professor at Cal Poly, why is factorial of 0, 1, and he says he can't tell me, but that's just an accepted fact. So if it's good enough for him, then I guess I will have to accept it too. All right, so 3 factorial would be 1 times 2 times 3, all the way up to this number, right? Starting from 1 equals 6. And then 4 factorial will be 24. Now notice these all have the 1 in front. When I do these, I don't write the 1, because 1 times that is still that. Okay, so this is 2 times 3, this is 2 times 3 times 4. You don't need the 1, because 1 times the 2, it doesn't do anything. That's just part of the definition of a factorial. Okay, write the first 5 terms of the sequence. So you're going to give me 5 numbers starting with n is equal to 0. So if n is equal to 0, what would be the first term? Try and write these out. Okay, so you have 2a to the 0, a sub 0 is equal to 2 to the 0 over 0 factorial. Remember, 0 factorial is 1, right? What's any number to the 0 power? That's also 1. So the first term is 1. So I need 4 more. I want 5. So I plug in the 1, and I get 2 to the 1 over 1 factorial, which is 2. And if I put in a 3, or I'm sorry, a 2 for the third term, 2 squared over 2 factorial is 2. So I have a 1, 2, and a 2. What about the fourth term? 3, 2 to the third power is 8, and 3 factorial is 6, so it's 4 thirds. And then the last one I need, the fifth one, use a 4, 2 to the fourth is 16, and 4 factorial is 24, so it gives me 2 thirds. You notice that these are getting smaller. Okay, but this is kind of an interesting sequence. So if I give you 1, 2, 2, 4 thirds, 2 thirds, and told you to come up with the nth term, that would be a pretty tricky problem. All right. All right, let's see. Let's use these factorial notations. I have 8 factorial, 2 factorial, 6 factorial. That's a lot of stuff to write out. And then to put in your calculator, right? 1 times 2 times 3 times 4 times 5 times. So there's a little shortcut for doing these. If you write them all out, and you know anything about reducing fractions, you can reduce this before you have to multiply them out. So I'm going to reduce the 1 through 6, because I have a 1 through 6 in the numerator and the denominator. And then I have a 2 and an 8, which I can cancel that and make a 4. So this all becomes 7 times 4. You see how I can do that without even a calculator, right? So let's try this one here. So you have 2 factorial, and notice now I'm not writing the 1 anymore because that doesn't do anything for multiplication. So I'm going to just cancel some of these out. What can I cancel out? The big chunks first. Let's cancel that, the big chunks there. And notice that 2 times 3 is 6, so I can cancel that. And I'm left with 2. So pretty simple. Now, these are the ones that always gets people. Okay, this is n factorial over n minus 1 factorial. So that means all this starts at 1, 1 times 2 times 3 times 4 times 5, all the way up to n. This, let's say n was 5 or something, right? Go up to 5, and this would be going up to 1 less than 5. So this would be like 1 times 2 times 3 times 4, right? So what if n was 5? Wouldn't you write it like that? So you just cancel them, and you get 5. So this is just a way of trying to figure out what might this equal. It doesn't really equal 5 because I said what if n is equal to 5, but it's not 5. So what do you think that would be? If you wrote this out like this, 1 times 2 times 3 times 4, all the way up to the one right before n, and you have 1 times 2 times 3 times 4 times all the way up to 1 before n, you can cancel all those out, and you're left with just n. Okay, this is really tricky, and it's part of what you have to know, so get used to looking at this and think about this real carefully before you end the video. Okay, all right. Okay, if you ever do this here and do a what if by plugging in a number, make sure you check a different number. Never use a number like 2, because 2 is a tricky one. Don't use 0, 1, or 2. 2 times 2 and 2 plus 2 will always trick you. So they both equal 4. You never can figure out which one it was. And 3 is kind of a little bit tricky too. A lot of people get stuck with that one. So try a number like 4 or more. Okay. All right. So that's it. That's the end of the video. Please do the Google form.